Um, I am John Handler. I'm a Senior Principal Solutions Architect with AWS. I'm joined with Bobby Mohammed, who's a Product Manager for OpenSearch Service, and Ryosuke Sudo, who is a ML Engineer at Recruit. So we'll be giving you a talk today in sort of three parts. I'll take the first part, then Sudo-san will take the second part, and then Bobby will take the third part. So who here has actually bought a product on Amazon.com? Like everybody, right? But who here has done that without using the search engine? Yeah, like nobody, right? So when you go to Amazon.com, you have an intention, you have a goal, you want to buy something. And the search engine is how you express to Amazon.com that you want it. If you go to Google, you have something you want to know, you type some words in, and Google hopefully comes back with some helpful information that solves the question that you have. If you're building an application, all kinds of different use cases across things apart from e-commerce, document stores, all of these things, we mediate between our intentions, our desires, and what the application knows through search. And that has been, traditionally, until recently, that has meant that we've used words to communicate to the search engine what it is our intentions are. Now, obviously, we have huge step change in the world that has changed how we interact. Now we expect more from our information retrieval systems. We expect them to be able to interpret and understand what we're saying. So we're going to talk a lot about that today. The problem with search engines, or one problem with search engines, and you probably all have had this experience too, you say like socks for children, and you get random stuff. Some of it's socks, some of it's children's toys, and there's a mismatch between what you expressed and what you got. Really what's happening is, until these new technologies, search engines have keyed on words and have done word-to-word matching. So here's an example. You know, I said like, all right, I want a good TV to watch sports. Now, I know that that means fast refresh, very bright, very sharp picture, but those are not things that I actually typed into the search box. And even if I did, perhaps the people who were describing their TVs would not have actually used those exact words, right? And you can see here, there's a bunch of search results. Mostly what it keys on is the word TVs, right? So with the newer technologies, we're going to talk about how we get to a better way to do retrieval. Who is familiar with OpenSearch? Anybody? Oh, great. A lot of familiarity in the audience. So OpenSearch, community-driven, open source, suite for AI-powered search and log analytics. The project itself has open governance under the Linux Foundation. We have some of our premier members, AWS, IBM, SAP, and Uber, as well as general members of the foundation. It is open governance, it is a vibrant community, and it is going gangbusters. And of course, we have our Amazon OpenSearch service. So if you want to run OpenSearch in the AWS cloud, Amazon OpenSearch service, first of all, makes it easy for you to deploy and operate OpenSearch in the AWS cloud. Second of all, we have performance gains, both in the open source project as well as in the managed service. 6x from 1.3, I think this slide is old, 2.19. We have more performance gains in 3, which is live now. We also provide a number of different options for cost efficiency, knobs and ways you can tune, either for vectors or for log analytics. And we're going to be talking about those later. We also have a number of integrations that make it easy to move your data from other AWS services to OpenSearch service. I'm not going to hit these too hard. OpenSearch itself is a distributed database system. It runs on a set of nodes. Data nodes provide the storage and request processing. We have our cluster manager nodes. They orchestrate the cluster. We have our coordinator nodes. They coordinate request processing. And we have ultra-warm nodes that make it that let you tier out older, especially log data. We also have a serverless offering. Serverless offering, you just create a collection, and the collection is a collection of indices. You use REST APIs to send your data. In all cases, we front the cluster with some kind of load balancer, and you send your requests to OpenSearch. OpenSearch is a REST API, so it's all JSON-based, very, very familiar. So as I was alluding to, if you're building a search application, chances are you started with lexical search. You maybe put some data into OpenSearch, and you're using the lexical query with BM25 scoring to get results for that. But with all the new technology, we have all this demand and drive to include semantic search. And semantic search up levels, and large language models, embedding models, are able to pull out meaning from strings of text. So we have a lot of this like, okay, well, I have this lexical search, it works pretty well. I have this semantic search, it works pretty well. But ultimately, we see the world coming to this kind of hybrid model where you want to have the benefits of lexical, the benefits of semantic, and blend them somehow. So I'm going to take the first part of the talk to talk about this. And then the newest thing is Agentic. With Agentic, you have an even better way of building search results from queries. All right, so let's talk about the journey from lexical to hybrid. Lexical search, again, is very good if I know I want the Samsung 64-inch OLED, blah, 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 and I type those words, I can match those words, and I'll get a search result that's a good result. So it's good for very specific queries, but it's bad for more abstract queries like, I want a TV for watching sports. When you use OpenSearch, we start with the search document, so the lexical sort of journey begins with the search document. As a design point, when you're using OpenSearch, first you figure out what you want to retrieve, then that's what you put into OpenSearch, right? So this search document, it's a bunch of JSON. This is an example from the Amazon product Q&A public data set. It's a question. It has some information about the product. It has answers for the question. All of this goes to OpenSearch. OpenSearch creates indices for each of these JSON fields, enables fielded matching for that content. So when we do lexical search, the first thing we do is we take blocks of text and process them according to language-aware analyzers, right? So if you look at the number 22 over there, the Tickle 98-inch Q65 QLED 4K, blah, 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 you can see in there are some kind of weird-looking words like larg and Dolby with an I. All of that is language processing, and the purpose of that is to make it easier for queries to match those words, right? Runs, run, running. It's all the same word. A query that says any of those should match that. So there's a stemming that goes on. We remove common terms, those are called stop words. We add synonyms to enable better matching. Now the second one there is a TV frame, actually, not a TV. And this query, large screen televisions, ought to match the first one better than the second one, right? So we have to analyze the query as well. We changed the text that we indexed, so we analyze the query as well. Within OpenSearch, core data structure is an inverted index. Inverted index maps every term that's been seen in a field to the documents that contain that term. That's an efficient way to set up for retrieval. So when we have the terms large screen and television, we just go look up in the index those terms very fast, and we have the set of posting lists. That's the documents that contain them. We apply the query logic, in this case an OR, so we take all of the documents with large, screen, and television, and we OR them together and we get 1, 3, 12, 18, et cetera. The next thing we want to do is score them. And the basis, one of the core features of a search engine is to provide a relevance value that helps sort the possible search results into the desired search results. And this is the kind of core of what search engines do. So how do we score? Well, the first thing we do is we look at all the words. How common are those words? Something like television, let's say, is less common across all of the documents than, say, large. Large is going to be a very common word. So television gets a higher score than large. We then multiply by how many times it matched in each of these two example documents, right? We multiply together, and that gives us a result. In this case, we see that indeed document 22, surprise, surprise, matches a little bit better than document 38, right? And so this is the desired result. This is what lexical search is. This is all lexical search does. Like I said, we're matching words and we're scoring based on the value of those words. With semantic search, we are using models to get at the meaning of strings of words, right? So if you think about it, like a word itself is already carrying meaning. So matching word to word, we already have some small window of meaning. Now we've expanded that window so that when I say large screen television for sports viewing, the fact that sports viewing and large screen television are close together enables us to bring in that large screenness to the sports television into the large screenness, right? It lets the model bring that together. It's not good at specific queries, though. If I say like this tickle 98-inch Q65 blah, 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 I don't want it to try to understand what I mean. I just want to put those words in and get an exact match, right? But it is really good for contextual kind of information, and it's good for multiple modalities, for multiple languages, all of these cases where meaning is what you want to match. So when we start with our document has a little bit of a journey, right? We have some portion of the document that is textually representing what that document is. In this case, you can't see it, it's tiny. It's the product description. I take that out as a chunk. That chunk I then send to Bedrock or SageMaker or some other model technology to generate a vector embedding. I add that vector embedding back into the document, so you can see there I have it in pink. The vector embedding is there. I then ingest that document into OpenSearch service. In this case, I was using OpenSearch ingestion. So how do we decide which is a better document? Well, vector embeddings, they're just big areas of numbers. They're vectors. They create a multi-dimensional space. And when I ask a question like what TVs are good for watching sports, I create an embedding for that as well, and that will live in the same space as all of the products and documents that I have. So I project that into the space. I then find the nearest neighbors. Closeness is the measure of similarity for vector search. So closeness is a kind of nebulous concept, but we can put some definition around it. So let's say I have these three vectors. The first thing we can do is do a Euclidean distance. The darker one on the left top is the query vector. The other two are document vectors. So I can take a Cartesian distance between those and I can say, okay, well, this one is 3 times farther away than that one, so that one's closer, right? We also can use cosine. These are common similarity measures. We can say, okay, here's my 3 vectors again. The query vector's in the middle, and we can look at the angles between the vectors to decide which one is actually closer. And the one on the bottom, twice as far away in cosine world. So I want to introduce you to the neural plugin, if you don't know about the neural plugin. OpenSearch's neural plugin provides a bunch of different things that make all of this semantic processing easier. The first of those is there is a connector library that enables you to connect to embedding models that are external, also large language generating models. So we have a connector framework, and then we can define, or you can define in OpenSearch, pipelines so that as you ingest your documents into OpenSearch, through the neural plugin, OpenSearch calls out to the embedding model, gets the embedding, and puts it on the document. This simplifies the ingestion. There are lots of ways to do ingestion. We'll talk about other ones. But this is a simple way if you want to get started quick and test. Similarly, on the search side, we provide a number of different processors that enable you to create a query embedding with a neural query, and you send the text and a model ID. OpenSearch does the embedding for you. So to engage this, you're going to use an ingest pipeline, and that's a simple put ingest pipeline blah. You can see there's a field map in there. It says, for this field, create an embedding and put it in that field. Super simple to use. You pass a model ID. Model ID is the reference to the connector that tells OpenSearch which external model host to call. You put that into your mapping. Now, OpenSearch behind the scenes is kind of databasey in that it has a schema for every field. The schema tells it how to process that field. Like if it's text, cut it up, apply language stuff, all of that. Once you've defined the pipeline, you just set that as the pipeline for your mapping, and OpenSearch automatically, again, calls out and creates vector embeddings on the way in. And finally, we have our query. So our neural query, here, again, we just say which field is the embedding field, and we give it the query text and a model ID. It does all the work to do that query. I'll mention really quickly, we do have a batch inference that we recently launched that enables you to use OpenSearch ingestion. That's a feature of the OpenSearch service to call out to Bedrock batch inference and embed all the stuff as it's going in. I'll also mention we have something called automatic semantic enrichment. This works with a different kind of embedding model, a sparse model, and it's completely automatic. You simply set the field type, and OpenSearch does the work of creating the sparse vectors for that field. All right, so coming to hybrid. So we saw problems with Semantic. We saw problems with Lexical. And so it's natural to say, sometimes I have really exact queries. Sometimes I have really semantic or meaning-based queries. I want to do the best of both of them. It's not, you're not going to look at it for everything, but it's really good for most search use cases. And in some ways, this helps you maintain a stronger relationship between the text and the meaning of the text. In OpenSearch, it's pretty simple to use. Hybrid query like this, you have the query itself, and then you have 1 to 5 query clauses. Each of those clauses then runs in parallel. In this example, we have a neural query and a sparse query running both of those. That could be a lexical query as well. We're running both of those, and then we need to blend the scores. So how do we blend the scores? Oh, first, we have to create a search pipeline. The search pipeline tells OpenSearch how to blend those scores together. This example is using a normalization processor that's doing a numeric normalization of the scores and then comparing them or blending them that way. So how that works in practice is, let's say I have query 1, and those are the scores on the left, and query 1 is a lexical query. So I got 412 and 396 and all of that. And then query 2 is a neural query, and I'm using cosine similarity, so my score range is 0 to 1. Clearly, I can't just put those together. So with numerical, what I do is I put them in I normalize them to the same scale, and then I average to get the result, right? And so that gives me a final ranking like that. The other way that you can do this is called reciprocal rank fusion. Reciprocal rank fusion looks at the slot that each result is in, and then gives a weight for closer to the top, descending, and then combines based on the weights for the query, for the result position, right? So with RRF, you actually get some benefits. If you have outliers in terms of the scores, they don't affect as much. It's a much more stable way to go about this. So kind of wrapping up this little section, we have some standardized corpora here. So NF corpus, Arguana, Fika, Trek, Covid, Sidox, and Quora. You can see the lexical score This is NDCG at 10. So this is the normalized discounted cumulative gain. And what that means is the higher up you are in the results, compared with the ideal set of results, you get more points. So it's a scale of percentages. This is not a scale. You get better as you more closely match the ideal search results. Okay, so we have our lexical scores there, hybrid with numeric combination, hybrid with RRF, and then a bunch of percent differences. The thing about these is it is super hard to even move 0.1% on these standard measures. So if we look at something like the Quora or Fika workloads, those are both question and answer workloads, by the way, where we get up to like 12 or 13% improvement with RRF. That's a huge result. So we're seeing a lot of benefit of doing hybrid. Now, of course, some of them are a little bit worse. Most of them are better, right? So that's what I got for you, and just sort of seeding the thought about lexical, semantic, and hybrid, and how to use each of those, and what the benefits are of picking usually hybrid. I'm going to ask Sudo-san to come up and talk about how they do that at Recruit.
Okay, so hi everyone. I'm Ryosuke Sudo. I'm a machine learning engineer at Recruit. This is my first time at re:Invent, so yeah, I'm very excited and a little nervous, but I'm okay, yeah, so I will enjoy these situations. So today, I want to talk about our hybrid search systems. Yeah, so why we need hybrid search and how to build it. Let's get started. Okay, and this slide is one of the most important slides today, yeah. So our legal team asked me to include, yeah. So the key takeaway is we are good guys, yeah. No personally identifiable information was collected and stored or used for training, yeah. So our legal teams are happy now, so let's go next, okay. So this is our company, Recruit. We operate many kind of fields, from jobs to travel and beauty, yeah, any more. You might know our global brand like Indeed and Glassdoor, yeah, they're part of our company. And today, I'll focus on one of them, restaurant search service in Japan, Hot Pepper Gourmet. This is a Hot Pepper Gourmet, one of Japan's largest restaurant search and booking platforms. We are #1 in both the numbers of reservable restaurants and online reservation users. We handle hundreds of thousands of reservations every day, and we operate also tens of millions of users monthly, yeah. So mostly users starting from search box at the top, improving search quality is key to our success. Let me walk through our search challenges. Our original search systems relied heavily on lexical search. You might call traditional keyword matching systems. For a long time, it had great RAM, but it had obvious limits. For example, imagine user wants sushi restaurants. Yeah, that is great. If they type it perfectly, lexical search match correctly. But what if they make a typo, like sushi restaurants? Simple lexical search can't match sushi to sushi. So lexical search is fragile agent against typos. And these problems get way worse in language like Japanese, which has no spaces. To help you imagine what that's like, I'll just remove spaces from query. In correct query, sushi restaurants, our segmentation process correctly splits query into sushi and restaurants. That's great. But at one typo, sushi restaurants, our segmentation process breaks. Such or esta, yeah. Word is wrong, and number of words is also wrong. So lexical search is fragile against typos, especially in language like Japanese without spaces. You might think, yeah, hey, let's use vector search. It's semantic and it's handled typos better. Yeah, you're right, partly. I will share another scenario. Here is user query, Sushi Hero, yeah. And there are two candidates, Sushi Hero on Strip and Sushi Magic. And we are using state-of-the-art M&E model. Yeah, you might know starting with G. Yeah, that's a very strong large language model. Yeah. You might think this is a very easy problem and vector search success. Let's look at the result. Number one is Sushi Magic. Why? Even we use state-of-the-art large language model. Because vector search focuses on meanings, not keyword. So the word magic has context-less, but word on the strip has strong location context. So strong location context ironically pushes correct answer further away, rather than completely different restaurant names. So that is limits of vector search. This is a quick summary. Lexical search is precise, but struggle with typos and segmentation. And vector search is semantic and context-aware, but it can exactly match. What we want? We wanted best of both worlds. That is why we need hybrid search, precision, and semantic understanding. So let's get into the technical meat of how we built it. First, why did we choose OpenSearch? For three quick reasons. First, hybrid search capabilities, full text and vector. It's easy to implement, so we could focus on improving vector search model. And second, it's fully managed on AWS, ease of development and operations. Scalability and blue-green deployments, backups, and security, all are managed. It helps us. And third, it has rich ecosystems. It has managed ETL like OpenSearch ingestions, and it has also language-specific plugins. Yeah, it helps for Japanese people. Yeah, we also considered other options. Vendor E has rich features, but higher cost and less AWS integrations. And the Vendor B has a powerful, but yeah, it's complex to manage. And other vector DBs is great for similar search, but it's limited full text search. So for us, OpenSearch hit our sweet spot. Yeah, that's great. So let's next talk about our vector model. We use two-tower model architecture, one encodes for query and one for store restaurant information. It trained on our user logs and synthetic data we generated with large language model. Today, I'm not going to go deep into our architecture, but key takeaway is fine-tuning really matters. For our cases, fine-tuned lightweight BART actually outperforms large language models. So I recommend it. So if you're dealing with domain-specific vocabulary like restaurant names, don't just rely on off-the-shelf vector models. Fine-tune them. It makes it difficult. Okay, so next, after we get vector model, our first step was try to use the built-in hybrid search systems. It is very simple. We just write multiple queries in query field. That's very easy. We don't need any changes architecture. And it's very easy to implement, so we can focus on improving vector models. And it gave us many business impact, but we have realized that we could go even more further. To understand opportunity, let's look at our hybrid search, built-in hybrid search systems. In built-in hybrid search systems, OpenSearch first takes lexical and vector results in parallel and normalizes, and after that, merge them into single score before ranking. That is a problem. Because when both scores are high and both scores low, that is okay, clear. But vector score is high and lexical score is low. In case, that means typos or paraphrase. And lexical score is high and vector score is low. It might the case means rare word or domain-specific vocabulary. So they represent completely different things, and which should be but more depends on user intent. So to handle this problem, we realized that our ranker needed vector score and the lexical score separated. That is our key insight. To solve this, we built custom hybrid search. In our custom hybrid search, our executor run lexical search and vector search in parallel and get both scores separately and feed them into our ranker. So our ranker can use lexical score and vector scores separately and also incorporate user logs and user intent other signals. Yeah, that's great. It enables us to make way smarter decisions and adaptive ranking. It's a little bit more complex to implement, but it gave us up to twice times improvement in top 1 search accuracy. So totally worth it. This is our final architecture. Our custom ranker moves out of OpenSearch and running in ECS container, and also our vector models running in ECS container. This setup gave us more flexibility and easy to make scalability much easier. Yeah, that's great. Let's look at our business impacts. We tested several versions from original and hybrid plus ranker. Finally, after launching custom hybrid search, we achieved a 10% improvement in number of bookings via search and 90% reduction in zero-hit searches. And yeah, that's great. So our key takeaway is properly combining lexical and vector scores led to significant business impact. So to wrap up, what worked well? First, managed blue-green deployment is great. Zero-time downtime scaling gave us operational confidence. And also, OpenSearch accelerates our experimentation. Yeah. And finally, seamless hybrid search ingestions is great. It enables us to launch quickly our first steps. And next, what's next? First, I would love for support building hybrid search with model-based fusion. Yeah, today I described. Yeah, that would replace our customer solutions entirely. And also, we need multi-vector search exploration. Yeah, multi-vector search improve not only semantic but also accuracy. So that is a key feature for us. And I was going to ask for support OpenSearch 3.3 support, but it was released last week. So yeah, so thank you for AWS. Yeah, so yeah. So yeah, that's for my presentation, and thank you for listening for my. So I'll hand it over to Bobby. Yes.
All right. Thank you, Sudasan. That was excellent demonstration of the value of hybrid search. Thanks for sharing with us all the way coming from Japan. Okay, thanks. Before I get started, quick show of hands. How many of you are doing agentic search or agentic retrieval in your applications now, experimenting or trying out? Can I see quick show of hands? That's a good number. And how about people who are deploying in production? Anybody deployed in production? Agentic agents or agentic workloads? That's good. More than I thought. 2 people. That's good. So we're going to cover agentic search. Basically, John introduced the traditional search and advanced search, how they can be used to improve the relevance. I'm going to cover agentic search, how OpenSearch is implementing many features to help with these kind of emerging use cases in the agentic AI applications. Before we talk about agentic search, I just quickly want to kind of understand how agentic workloads differ from traditional workloads. If you look at the traditional workloads, they are meant for humans and single query or short queries for millisecond kind of response times. On the other hand, the agentic workloads are kind of executing multiple dense queries, expecting real-time responses. And For that to happen, they have to use the agentic reasoning loop that is dynamic and iterative in nature. And the agentic reasoning loop has many components, as you see in the diagram there. It uses the LLMs, which is the brain behind this agentic reasoning loop, that leverages the tools and the data sources to enrich the context, and then it retrieves the information and kind of brings some results. And this process keeps iterating until it finds the right, it meets the goals for that particular job. And while iterating, it keeps updating the index so that the data is fresh in the index, and keep updating all the actions accordingly. So for the agent to run these iterations and extract the right context, retrieval is the foundational layer to make that happen. And for the retrieval, if you don't have a good retrieval, the amount of time you spend in the iterations and the context that you have will be not suitable, and the relevance will be very poor. So force-fitting the traditional search methods onto agentic workloads will lead to poor relevance, and also you're kind of wasting a lot of money running many iterations and trying to retrieve unnecessary context. So how the industry is approaching to enrich this context, there are multiple approaches people are taking. The first one is LLMs. Why can't we just use LLMs to enrich this context and enhance the relevance that you can get with the search results? So if you really look at last 3 to 5 years, or the Gen AI or the Agentic, all this explosion in these use cases is primarily driven by the innovations happening in the LLMs. And they are getting smarter and smarter with each iteration of the LLMs. And the primary driver for them to make them smarter is, in these agentic applications, we want to make them model-driven. And the models are smart enough to decompose the task and execute all the steps that you have seen in the agentic reasoning loop, so that you don't depend on external tools or anything. But the problem is, and the way they are doing all these LLM vendors is enhancing the context. If you really look at last 1-2 years, the context windows have exploded. It used to be in a couple of hundred or 1,000 tokens, context window size. Now you see in millions. And basically, you can hold a couple of pages of information with few hundred tokens. Now you can hold like thousands of pages, which is great. That means you can really enhance the context, hold a lot of information, but it has its own challenges, right? So if you really look at the agentic workloads, if you have run the test cases, the POC or the experimentation phase, mostly those are lightweight agents. You try with few agents. The context window that you see with these LLMs is sufficient to handle those kind of jobs. But if you really get into production workloads, these agents are getting into hundreds, if not thousands of agents, and the context window that you have, like millions, is not enough. That means you need additional mechanisms to hold this information. So basically, they cannot hold all the information. And the second one is the retrieval quality and the latency. That's a challenge. Just like humans, we cannot hold infinite information. After a certain point, I keep talking to you, you will stop listening to me. So just information overflows. For the LLMs with large context window, it's the same problem. There is so much context. As you try to retrieve, the quality of that retrieval doesn't meet the mark, and also you will spend a lot of time to retrieve that information. So that's the second challenge. Just increasing the context window forever doesn't solve the problems. That's the point. And the third one is context management, right? So as you have this context between the short term or the context window and how you process this information, there has to be a mechanism to really move that information back and forth between this memory hierarchy. So LLMs cannot handle that, and you need some external mechanism to do that. And that's why we have seen last few years, right? So there are like popular design patterns like RAG and agentic search that really evolved. And so if you really look at RAG, RAG is the most popular use case that I have seen last 1-2 years at AWS. We get to work with hundreds or thousands of customers, and they really benefit if you have a single query, a static system. And we have built rich set of capabilities within OpenSearch vector database to enable these RAG use cases. And that's why we are the a most recommended vector database for AWS, and also the default vector database whenever you use Bedrock knowledge base. So because we have these rich set of capabilities, and also we give the price performance to make this context augmentation using RAG design pattern. So like I said, the primary problem with RAG is it can't reason, it's very static, and if it is a single query system, it works really well. So given these limitations, we kind of see all these search use cases slowly moving towards agentic search. And agentic search is primarily, a retrieval is driven by reasoning. That means it can leverage the agent reasoning loop, and whenever you do a dense or multiple vectors, it has the intelligence to decompose that complex query and kind of create subqueries, if necessary, DSL queries, so that you can find some results that are very relevant for your search. And another benefit with agentic reasoning loop is it can really enrich the data by talking to a number of tools using the MCP protocol, and also it can extract a lot of information from multiple data sources. So you can retrieve the enterprise data, and if you need to retrieve external data, you can use the MCP to enrich this context. And as you enrich this context, you need to have the ability to store this information because the volumes will grow, and you need a memory management, a memory hierarchy. And that's why for a agent reasoning loop, if you have the ability to manage the short-term or the working memory and bounce back and forth between the long-term memory and make that judgment very smartly so that you have that information when you need it. When you don't need it, push it to the persistent long-term memory, and that way you manage the valuable short-term memory to do the job at hand. So that's why agentic search has tremendous value when you have a dense query system, or when you're looking for a multi-ton system where you need to go after and think and solve these problems. That's why we kind of invested in this feature with OpenSearch 3.3 and also with OpenSearch Managed Service. You have the out-of-the-box experience with agentic search. And the way I just highlight some of the key capabilities here, there are more to it. The first one is a query planning. As you receive a agent receives a query, it could be a very complex query. So we kind of built a query planning tool that can break down these complex queries and translate these natural language queries into DSL queries and does the heavy lifting for you. And the second one is the AI-powered intelligence. So the benefit of OpenSearch is it has a rich set of search capabilities. It has a rich set of quantization capabilities and others to save the cost and the performance for you. But it also creates burden for our customers because they have to think through which one is making sense for me, when to use what. It brings some complexity with it. So with agentic search, we kind of added this layer, AI-powered intelligence, where based on the query type, based on the user intent, the agentic search module can pick and choose which aspects of quantization, which aspects of search make sense so that they can apply at the right time for the right problem. So that is the intelligence layer that's really useful. Even some of the things that John mentioned, scoring, what kind of search technique you want to use, lexical, semantic, or hybrid. So underneath, there are many filtering techniques. There's many things you can use with OpenSearch, but this layer does a lot of simplification for the user. And the third one is flexible and customizations, right? So with the ability to work with the MCP, both with the internal data and also the external data, you can customize your search index with what kind of information you want to keep within your index. And what I mean by that is you can add tools, you can add data sources, you can customize the context that you want to deal with. You have that complete freedom to pick and choose. And you can go to hundreds, or if not, whatever makes your application useful. And the last one is accuracy, especially when you have multi-turn applications. Agentic search really makes total sense and really gives you that additional benefits with relevance. So to make agentic search work, there are many components that goes into. As you have seen, there is a memory. There is how do you work with MCP server, and there are can you deal with multimodal embeddings. So there are a bunch of capabilities we brought with OpenSearch 3.3 and also in the managed service that you can leverage to build this agentic search either out of the box experience, or you can put together an agentic search solution by yourself. So I'll quickly walk through these 4 capabilities here, and there are more, but I just want to quickly highlight so that you know what's there so that you can leverage for your application. The first one is the multimodal embeddings. Why multimodals? If you look at most of the organization data, we know it's unstructured data, it's very fragmented, and it's very siloed. If you take a medium-sized to large-sized organization, you'll have hundreds of developers building applications. Each application kind of brings you data in different modalities, and the ability to tap into those modalities is super critical. And if the company or the organization cannot use these all modalities, basically there is so much hidden information that's missing out. So that's why if you see the LLM vendors, they invested quite a bit last 1 year. Most of the models that you see are multimodal generative models or multimodal embedding models. And to make this happen, we kind of worked with Amazon Nova model. If you look at OpenSearch, we already kind of taken this path of multimodal last year itself. We support text and image with the Titan embedding models. Now, with Amazon Nova multimodal embeddings, we support 6 modalities that we integrated natively with OpenSearch. It's a very intuitive, easy to use experience, one click. And the main thing with this Nova multimodals is a unified embedding space. What I mean by that is when you have multiple modalities, you can create a vector embedding space for each modality, and you can store them separately. But with the Nova multimodal, it unifies all these modalities. You kind of build one embedding space that's unified, and also you bring together the semantic understanding or the relationships between these modalities. So what's happening is you have a rich context. You like humans, we kind of perceive in many ways, audio, video, and also visually, and we kind of make sense of that. Now the context that you have is really enriched. And the second benefit is because you are saving in one embedding space instead of multiple embedding spaces, your vector storage is also smaller, and you are saving cost on the vector storage. So that's the benefit with this Nova model and the integration, and you can quickly access to build these next-gen applications that are multimodal. And the next one is MCP, right? So we heard this last 1 year. A whole industry kind of accepted or recognized this as the standard protocol to work with agentic systems, to access the external data or the tools. So to enable this, OpenSearch also built MCP client and server that you can use based on your needs. And also we built a lot of ready-to-use tools. We have about 20 tools that you can tap into based on your application needs, like query planning, search index, and so forth. And we continue to build more tools so that you don't have to invest time to build these tools that you can work with MCP. And the third one is authentication and credentials. The moment the MCP came into the industry, the biggest concern for many people is, hey, I'm giving access to my data to external system. How is my authentication? How secure is the data, right? So we wanted to address that head on. So we kind of provided a configurable credentials based on the session or the user. You can give permissions and manage these security boundary when you're using MCP server with OpenSearch. And on top of that, in the agentic applications, it's a very early. And there are many frameworks people are using. Everybody has their own preferences, and winner is yet to be declared. So just to play with the ecosystem, we integrated our OpenSearch MCP server pretty much with all the mainstream vendors that you see here, like AWS Strands, Crew, and LangChain and so forth. And you can, if you go to use those frameworks, you can just quickly use the OpenSearch MCP server. So that's the MCP. And the third building block is the memory. Memory is very, very important. It's a backbone of intelligence. This is what it makes agents stateful. So if I were to highlight few key benefits of having for agents is, one is the knowledge retention and retrieval, right? So if you have a short-term and long-term memory hierarchy, and you have a ability to store vectors, like I mentioned before, that are immediately required and persist them for future usage, that really gives you that flexibility to enhance the context. And the second one is the personalization. So because you have this memory, you can store every user behavior and their actions, and you can store per session or across sessions, and also you can store over a period of time. That really gives you the ability, when I am searching, the system knows what are my preferences and gives me the more targeted results. So you can really hyper-personalize if once you have the memory module integrated. And the third one is adaptive intelligence. What I mean by that is, because you know preferences, you are very context aware. The agentic reasoning loop that we discussed can deploy right set of tools, right set of tasks to really solve the problem at hand. And based on the user information, it can change the tools as well. So you are highly context aware, and you can be adaptive with your actions and tasks. So we also built agentic memory with OpenSearch as a memory API. You can access that if you are using within OpenSearch, or you can access that using MCP as a tool. So the memory API has ability to store short-term memory, long-term memory, session memory. We also store all the event history. That way you are not missing out any actions that were taken within the agentic system. And the way it works is, once the raw agent passes the raw messages, it captures them, and it has the ability to run memory operations like add, delete, or whatnot, and so that the information is up to date. So once you have the up-to-date information, you can decide to represent either in the dense or sparse representations, because it's a trade-off between quality and cost. When you go to dense, you get a lot of quality, but if you're trying to trade off to save the storage and the cost, you can go to sparse representation. And also, it's a very multi-tenant. You can configure the memory per user and really store all this information based on your enterprise, how many users are there. You can give them certain specific access to the certain memory boundaries, okay? So I strongly recommend give it a try. It really makes your agentic application smarter and wiser. And the fourth building block we have built is the specialized agents, right? So what it means is we are giving local agents within the OpenSearch environment. You don't need to go to some third-party agentic platform to build any applications. The benefit of giving this is you have access to OpenSearch data. You'll be within the OpenSearch cluster environment. Whatever permissions you have, you inherit the security and the security boundaries for that user. And also, you will have the observability that comes with it. You can look at logs and traces. You can understand what's really going on. So it's a really quick to use. All you have to do is few lines of code. You pick your agent, and you're good to go. And these are production worthy as well. So basically, within OpenSearch environment, you can pick the local agents and deploy them to meet your needs. Just to give an example, a flow agent is very good if you are trying to do some RAG pipeline orchestration. It can get you started really quickly. And the conversational agent is something, if you have a chatbot or conversational application, it can help you to build that really quickly. And the third one here is the plan, execute, reflect agent. So if you are trying to build something like a deep research agent, which is exploratory in nature, going after multiple resources, trying to think and explore and find the best answer, this can help you to build that kind of solution. So, and we are going to build more of these specialized agents to make the user experience easier looking forward. So that concludes the agentic search of what we are doing there. There is a lot of interest. Some of our beta customers already tried some of these features. We are going to invest. We are already working on some more new features. Looking forward to share those in near future. So I'm going to change gears really quickly. We talked about different kinds of search techniques and how OpenSearch is building these capabilities. Most of these capabilities will be running on the OpenSearch core engine. If you don't have the performance the core engine offers, all the things that you're applying, you may not benefit that much. So we always invest quite a bit of time. How do we optimize the performance? How can we get the extra boost to your performance? So if you look at this chart compared to 1.13, which is released a few years ago, we already kind of boosted about 11x core search engine performance, which is significant. And also, vector search is a very dominant workload for us, and we kind of improved that performance by 2.5x. So this is all with the latest release 3.3, and we want to make sure the performance is what you're looking for. And on the cost side, right? So if you really look at vector search workloads, the workloads are exploding in size. They used to be in billions. Now they're kind of transferring to trillions of vectors. And more we talk to customers, every other week we hear it's becoming common. To enable these such large workloads, the memory footprint really becomes a challenge. And how do you manage the memory footprint while giving the performance and the cost benefits is a problem on the table. So we already have the exact KNN, ANN techniques where it gives you most accuracy and also high performance, right? We added disk mode, which gives you that additional cost advantage when you have a large scale storage to make for these large workloads. What disk mode does is it has the ability to manage the vectors both in RAM and also disk. You store the high precision vectors in the disk, and you apply quantization, and then you store them in the RAM. So you use the combination of these and kind of save the cost while maintaining the quality of those results. And the last one we made in this tiered vector storage is S3 vector integration. As you all know, S3 vectors are the lowest cost way of storing information. And this year they introduced vector storage capability. And we natively integrated S3 vectors with OpenSearch. You can work with managed service, OpenSearch managed service, or OpenSearch serverless, and store the information in S3 vectors while taking advantage of OpenSearch search capabilities. So it's a good, powerful complementary strengths to kind of leverage and build the applications that are at massive scale. So that concludes all the things that we wanted to discuss today. Just to summarize, right? So OpenSearch search relevancy is front and center of search, right? So to give you guys best relevance, we have been investing quite a bit in all types of search techniques, and you have a choice to make. And each search technique is applicable for a specific use case. And lexical search is not going away. Semantic search is not going away. And on top of it, based on the complexity, you can apply agentic search. And like I shared with you, agentic search, we built multiple capabilities. I strongly recommend to give it a try, and I'm sure you'll find it useful for your advanced applications. And the third one is the cost structure. Like I mentioned, we've been investing quite a bit to improve the performance and also to give you the best cost structure to deploy these large-scale workloads. And if you upgrade to 3.3, you get all these additional features and also the performance benefits. And the last one is easy integrations. We strongly believe to work with all the services within AWS. We are natively integrated with services like Bedrock, SageMaker, or Agent Core if you're building GenAI or Agentic applications. And also, we are doing a lot of third-party integrations. If you're building any search applications, we want to make sure we are part of the ecosystem. Either you build within OpenSearch and work with those partners, or you build applications with the partners and leverage OpenSearch so to build those applications. Okay, so we try to compress a lot of information, right, with 1 hour. So there's more to do. OpenSearch is a very broad service. We continue to build and innovate. So if you want to learn more, get more hands-on, or dive deep into OpenSearch, I strongly recommend to read this book. And it's written by our friend John and other teammates. It covers a lot of things. It's a very dense book. It has a lot of details. I strongly recommend you get a copy of it. And if you want to get lucky, you can visit both, give it a try. You get a free copy perhaps. We have a bunch of them at the booth. And also, we talked about a lot of techniques today. If you want to see them in action, live demos, and also our partners are doing a bunch of things, you can see all the things we talked in action at the booth. Please go ahead and check out the booth and so that you can see them in action. And on top of it, if you want to build skills, like AWS is many services and too many choices. There's so much to learn. I strongly recommend you can check out the skill builder. You can double-click on any particular area of your choice, any service, OpenSearch or others, to learn and develop your skills. And last, right, so please give us feedback. We work hard to bring together right content and also the information that's useful for us. It will help us to iterate and make sure we bring the good content for you for the future sessions. And thank you for your attention, joining us, and thanks. Have a good reInvent.